I'm giving here a little bit of an overview of what we are doing in Bern. And this is also carved by Mihai Petrovici. We are co-leading actually 2 labs together here. And he introduced me to this field of neuromorphic engineering. And I came with my bio-math background and together work on this topic. And here are all those people that did contribute to this overall ideas of bringing physics, biology and computation together. And we're going to hear 2 talks today, Jacob Jordan and Elena, and one later also tomorrow by Julian Goetz. And I'm telling you that we get inspired by physics, and after all, computation is by a physical device. Here we have this computing device, and we have computation, and that I'm seeing as a cognitive landscape where our computing device has to target at some point. And of course, this computing device, as we know, has physical inspiration and eventually physical embedding, but also biological inspiration, as we are always hearing. And the point is that eventually, we have to go down, gradient descent, the kind of this big eagle, modern eagle, is the thing that is helping us to do good modeling of cognition. And the physical theories behind are certainly important because this is a physical device, but also because with these physical theories, you have a tool in the hand to describe dynamics in real time, as we heard in the talk before. So we let us inspire by this least action principle. We're not the first. On a high level, least action principle was suggested to, in fact, help us to understand cognition. Here we're going down with this least action principle to really understand neural dynamics and eventually, hopefully, also cognition. And as I was saying, we have other talks that can be embedded into this bigger framework of least action principle. The next one by Jacob Jordan on the gradient descent with conductances, so what real neurons have. Then we're going to hear immediately afterwards, a talk by Elena Kreutzer on natural gradient with spikes, and Julian tomorrow is going to speak about gradient descent for the first spike timing. But let me come back to this idea of least action principle and give you a little bit of a high-flying overview, as we can see here. A few of you may not know how important this least action principle is to describe physics. And here we have these 2 impressive views, on one hand of the universe, on the other hand of our cortical universe on the right-hand side from the Human Brain Project. And we know that here we are close to unifying theories, how this works, and this least action principle plays a crucial role. Here we're far away from unifying theory, although, as I mentioned, there are clearly ideas on a high level, and we'd like to bring them down to those biophysical theories and maybe could make the link to artificial intelligence and hopefully to this neuromorphic engineering. And at some point can close up with this long successful history on the left-hand side of this least action principle. Okay, so how do we fly now with our neurons? Here we have a trajectory of a less virtuosic animal here, and how would that be described now in terms of physics? Here we have this least action principle from physics that would describe the trajectory of a mass point. And the idea there is that you take a kinetic energy minus the potential energy, and you claim that this time integral across this difference is stationary. So a little bit of deviating on the trajectory would almost either increase or decrease a little bit, but only to second order. This is stationary local. Locally, it does not change to first order. That's the point. And from that now, doing this calculation of getting local conditions when you are in stationary state of this least action, we are deriving, or others did derive, the first and second Newton's law. So telling that force is proportional to the mass times acceleration is that one, and the total force is sum up to zeros. These are basic laws, and we do derive similar basic laws for the neurons. And what do we have to take now? So here in physics, it's interesting actually that this is a stationary state only. It's not a minimum. That is very important. Minimas are boring. You are in the Death Valley. You have to be just at the verge, to be able to go in different directions. And this is eventually also expressed in our neuronal form of a least action principle. And here we take, to get into contact with these neurons, the dendritic prediction error as a key notion of what should enter in this so-called Lagrangian. And we are going to minimize the integral of the dendritic prediction error across all the neurons in our big network that can encompass the whole brain potentially. And now we can also crank the handle, and we can derive by classical methods the neural dynamics that follows from this. This is the voltage dynamics that has just one additional term, the error, because the error should be locally in a neuron so that synapses can profit from this error and can try to work down that error of their own postsynaptic neurons. And here we have the learning rule that is implicated in this type of error correcting learning. It's a almost classical rule because we can show links to SCDP and so on, and it is related to what Wolfgang Maas was saying, for instance, to this eligibility trace learning and so on. So it is rather classical, except that we have here a formal way to derive that. And we go, as I'm going to show you, to a new insight that we have not really backprop in this raw vanilla form in the brain, but other version that is even more interesting, I believe. So let me go on and now embed those kind of Newton laws into a network. And what is now the procedure? It's supposed to be a framework for neuroscience even in general. We start, of course, not with our neuron, simple one, but with a network that we believe is doing the job for cognition. It may have memory component, it may have a recurrent network component, a feed-forward component, and we write down the Lagrangian, the thing that should be minimized or should be stationary over time. Then we derive now these Lagrange equations that are called, then apply this neural least action principle, and we get the neural dynamics. So this is basically the trajectory of our bird, of our airplane, that is now moving. And we have to tell where it is moving. Here comes now the learning, the plasticity, to optimally find your spot on the cognitive landscape. We derive kind of error back propagation and more of that. And because it is a physical theory, we now have hints to implement those neural elements in physical devices. Because after all, those ones here are also working in continuous time, like these transistors here, like these equations that I was showing you here, and like those neurons here are doing. They have the membrane, transistors, you all know of that. And here we have a physical theory that is working in continuous time. And then we get inspired, how maybe we could modify the thing here, because we can interpret now part of this network as an output. We can interpret this as actions and so on. And this is the whole loop we would like to put neuroscience into to get inspiration from these dynamical systems and to do cognition. And so let us have a closer look to those neurons that I'm claiming they're able to incorporate in this.
Excuse me, are you sure that you still want to be on the same slide, or?
I'm on
no, slides are moving.
That's good. Okay, here is this inspiration. We would like to have dynamics across cortical layers, dynamics within cortical circuitry, so within interneurons, and also within the neurons themselves as the pyramidal neurons. And I would like to, again, have a little bit closer look of what those two guys did. They were introducing these Lagrange equations from this least action principle. So basically, this is a condition, what should be happen on a local scale to satisfy this least action on a global scale. And they find, starting with this form of Lagrangian, the local dynamics, as I was showing you, and this applies to many other disciplines. And now the question is now in neurobiology. How do we do that? And as I was mentioning you, we start with a task, a network, and come up with this Lagrangian that is formed by these dendritic prediction errors, and from there we derive these neural dynamics. And the key now is that these dendritic prediction errors that I would like to introduce you here. This goes back to all the work of us together with Matthew Arco. So this is now this error in predicting the somatic firing by the dendrite that enters in this Lagrangian. And here we have the top-down input that always tries to predict what comes as sensor input below. So inside tries to be matched with the outside world. And we have to adapt both the top-down input, these feedback errors, and also the forward W's to classify the classical picture. And as I will show you in the end, we also have this B that is going to be the pseudo transfer inverse. And now we go closer to this error correction. We have also interneuron circuitries. Those inhibitor neurons are themselves inhibited typically, but we can disinhibit them and then get an error. And here is the key idea. If the top-down input does not fully match what is entering here and cannot be explained away by this negative inhibitory feedback, then we have a remaining error. And this error propagates down to the soma. And we have now prediction error also on this forward tree, on this basal input. And those neurons are seeing more activity coming back than they were themselves producing. And they know, okay, to reproduce what's coming from top, I have to either increase or decrease their weights. That's the basic idea. And by that, they help to minimize that error. They help downstream neurons to minimize their error and so on. That's the key idea. We have written this down in these different works that I'm citing here with Shao and Sacramentos, and originally starting from that one here. And let's now go to a network and embed these type of neurons into a network, as we can see here, and formalize this according to this least action principle. Then we have to write down this energy. That is nothing else, again, than this local dendritic prediction error coming here in this form that is expressed here in those ways. And we have in addition a cost, a target that would be reached, and deviations from these targets are expressed as quadratic means and as cost. And the Lagrangian that we're getting is simply the sum of those dendritic prediction errors plus this cost. We are nudging the outputs, these are the output neurons, a little bit towards the target, and we're expressing the deviation as a cost. And now we again go into this formalism of least actions, and we derive all those equations. There is something before I'm going to the equation. If you consider a dynamical real-time systems, we should be aware that we are always late in processing inputs and waiting for the feedback that is correcting for an error, because everything is moving ahead while we are doing our job and feedback is late. So one idea is to already encode sensory stimuli prospectively. And for that to work, these neurons must encode prospectively. And if we go back to all the experiments that we also do in Bern, we see such a thing. In fact, if we inject into real pyramidal neurons sinusoidal noisy currents, and you measure the instantaneous fiber rate they're eliciting, those rates are advanced. It is as those neurons are smelling that you're going to decrease or increase again with your input fiber rate. This is old work. And we can reproduce those ideas with these classical Hodgkin-Huxley formalisms. Those two here from Cambridge, they already offer this formalism with this activation function, inactivation function to get to those features that if we apply this and if we allow us to identify the instantaneous rate as sodium conductance, we get such a phase advance as well. And with this, we have all together now to go to these Lagrangians and derive our neural dynamics. And we have also generalized variables. These are these look-ahead look-ahead voltages that are now due to this Hodgkin-Huxley formalism. So we minimize or we look for stationary equations for dynamics for these Lagrange equations in terms of the look-ahead voltage. And we do not get accelerations as in Newton's laws, because the currency these neurons are thinking in is the future voltage. And with that, we can spare accelerations and we get to classical dynamics that we have seen here with this additional error, and we do minimize the cost, and we do get error backpropagation all the way. And we can generalize this to conductances. You're going to hear part of that for a single neuron. We can generalize this to spikes. You're going to hear part of it afterwards. And we can include short-term dynamics in all this framework as well. So next, I'm going in a few minutes to show you a few applications. We can now apply these to reproduce some cortical dynamics like intracortical EEG that we have from patients, and simply reproduce those activities starting out from a few electrodes and reproduce activities on other intracortical electrodes, and simply trace those, predict in some sense, not into the future, but on each current time step. We can do, of course, the classical MNIST with them. Let's work with Dominic Dold. And the nice thing is now that we can present those letters just for a short time, say 10 milliseconds, the same time constant of the neuron. So these networks are constantly changing their activity, and yet we do a good learning that is comparable with what the best feed-forward network for backprop actually is doing, because we do approximate backprop. Here we have this plot, here the simulation time to converge, and here the comparison that we are doing this type of computation, learning, even with low presentation time, almost as small as the time constant of a neuron. Okay, and we do get nice receptive fields. And finally, what I was telling you, this is the last slide, we are getting more insights. So far, we simply used as backpropagating weights the transpose. If we also apply this least action principle to these pyramidal neurons, we are getting a learning algorithm for this B by simply now also locally applying this minimization of error. Here is this energy. We simply say that here we have the low-level activity, and what is going up and coming down again should match. That's this energy here. We're getting some some use of other work, say synaptic depression, telling that we can extract the presynaptic voltage. And by that, we're getting eventually a learning rule that minimizes this least action. This looks that way, and we can prove that this top-down weights converges to a new form of pseudo-inverse. We call that data-specific pseudo-inverse. This is the Penrose-Moore pseudo-inverse. It is of this form where this gamma is the correlation matrix. And actually it works. So across these simulations, it performs better than feedback alignment. It is in our hands, at least with preliminary data, as good as backprop. And most importantly, it learns to escape from flat gradients. And this is what we see for such a network size with 2 hidden layers and 1,000 number of neurons in then 2 hidden layers. So this is in red, the learning curves across several epochs of our backpropagation algorithm, pseudo-backprop, data-specific pseudo-backprop, as we call it. And you see, it may be bad and get stuck, but most of the trajectories, they learn to escape from these flat gradients. And this is better than typical feedback alignment that we can see here. It's also better than a naive pseudo-inverse with the Penrose-Moore's pseudo-inverse. We have data-specific pseudo-inverse as we learn this for the specific input data, and is almost as good as vanilla backprop. So in that sense, we think it's helpful for us to also to really try to apply those principles to the brain, to the cortex, and derive these learning rules and test them. And that's what we did. And the lessons I'm presenting you that are for us also from physics and biology. So there is this least action principle from physics that we can map to neurobiology. We can now calculate these prediction errors locally by local microcircuitries. We have links to Hodgkin-Huxley, to the biophysics, to have a correct in time prospective errors. And we have a new version of backprop, the pseudo-backprop. That's it. And again, I would like to thank all my collaborators that were helping here, mostly of those that directly influenced that, and also others in my group and external collaborators. Thanks much.